So this is the introduction video to the book that I am writing with Roberto Villaflor. So the first thing that will live in a course of algebraic topology, we first construct a manifold, let's call it X, by charts. So let's zeta1 going to some open sets in Rn, then another chart zeta2 going to another open set again in Rn. And so we built the concept of a C infinity manifold. And then in the charts, we have these integrations, fx1, x2, xn, dx1, dx2, dxn, and then using the partition of unity, we finally define the concept of integral, omega being in h ln the RAM x and delta being in h n x z. So here, this is an n form, and this guy is a C infinity function. But in general, we can replace this one with the differential n form. And so here, instead of just a dimension of x, we can put arbitrary m. So in the course of differential topology, we define this de Rham cohomology. And this one, singular homology. So, but we want to apply all this machinery to a projective variety, and actually X is smooth projective variety. And one over, so everything will be our complex number. 9066 Grothendieck observe that instead of de Rham cohomology, we can define something called algebraic de Rham cohomology, that in the course we will define it. And usually when we want to write the algebraic de Rham cohomology, we put this slash over C. In the same time, Grothendieck and the people around him, they realized that singular homology is something typical to topology, and there is no equivalent version of it in algebraic geometry. But their effort to translate this guy to algebraic geometry resulted in étale cohomology and crystalline cohomology. Despite the fact that we cannot define homology in algebraic geometry, we can still construct some elements of this guy. So from now on, assume that M is even number, and take Z a subvariety of X. Just for now, let's assume that if this is smooth, of dimension M over half. And this dimension is the complex dimension, so its real dimension will be M. So this Z is an algebraic subvariety of X of dimension m half and a real dimension m. And even in the course of algebraic topology, we know how to attach to this guy a homology class HM X Z. One of the things that it is not so clear in the literature, and with Roberto, we have written it explicitly in our book, that algebraic de Rham cohomology is canonically isomorphic to the classical de Rham cohomology, here M, when we consider X as a C-infinity manifold, and this de Rham cohomology with complex coefficients. So anyway, this isomorphism is not an arbitrary isomorphism. It is explicitly given, and this means that whatever construction, topological construction here we have, topological construction like coproduct, we can transfer it to the algebraic side. Algebraic, for example, algebraic coproduct. In particular, what we can do, we can introduce this kind of integration, omega in hm de Rham x over c. Since the topological cycles we cannot all of them recover by algebraic geometric method, so we just integrate over the homology class of the algebraic cycle. So the main objective of the course is the computation of these numbers that we will call them period of algebraic cycles. Here I have to mention a theorem so again, due to Grothendieck, something that we will do it, that this algebraic de Rham cohomology, actually you can define it for arbitrary field K, characteristic K equal to 0. And for our purpose, we will always assume that K is a subfield of C. And it was Deligne around the 1980s who observed that these numbers up to this 2 pi I factor, 2 pi I m half, they will be in K bar if X and Z are defined over K. So whatever you start from X and Z defined over a field, these number will be some will go to the algebraic extension of K. So one of our goals in the course is to describe all the applications of this number in algebraic geometry. For example, using these numbers, we can state the something called Hodge conjecture. So what is this? After Grothendieck's definition of algebraic de Rham cohomology, something which was done by Deligne, that we can define the Hodge filtration, which is defined in the harmonic side, purely in the algebraic side. This will be filtration of the cohomology, and it will go until Fm, and Fm plus 1 will be 0. And it turns out that we can define something called Hodge cycle. So Hodge cycle will be a cycle in H M X Z such that this part of the filtration over delta is 0. And it is a very simple observation that will make that the algebraic cycle that we had is a Hodge cycle. And then we will reach to this millennium conjecture that any Hodge cycle is algebraic. So for this one, I have to say that instead of just one variety, we have to take a combination of these variety. And something that also I forgot to mention, that not necessarily Zi smooth Zi can be also singular. And there is a way to associate to singular Zi also a cohomology class, either by Hironaka's resolution of singularities, or by using the Cherkanas method introduced by Grothendieck. The final goal of the course and the book is to put Hodge cycle in families, and when we put it in families, we will reach onto a concept called Hodge locus. And it will turn out that in order to study this Hodge locus, we will need many concepts like infinitesimal variation of Hodge structures. We will land on something called Grothendieck's variation of Hodge conjecture, and we will give a very stronger version of this conjecture, which we will call them alternative Hodge conjecture. And at the end of the day, the course is all the details of this, whatever I wrote here in this short video.